Hello everyone, my name is Raina D. Jute, and welcome to this week's LeetCode problem solving video. This week I worked through 4 LeetCode problems, and the goal of this video is to walk through the concepts and reasoning behind each one, not just what the solution looks like, but why it works, what mental model helps, and what patterns came up more than once. The 4 problems we're going through are group by, execute async functions in parallel, LRU cache, had no idea what that was, and top K frequent elements. They each touch on something different: data grouping, asynchronous JavaScript, classic computer science data structure, and frequency counting with a sorting trick. Some, if not all of them, were pretty new territory for me, so rather than pretending I have them figured out immediately, I want to walk through the reasoning behind the way I actually walked through it. So let's start with problem number 1, which is group by. So this problem asks you to add a group by method to all JavaScript arrays. You give it a function, and that function decides which group each item belongs to. The output is an object where each key is a group name, and each value is an array of items that belong to that group. So if you have an array of objects with an ID field and you group by ID, you get an object where each key is an ID, and the value is all the items that share that ID. The breakthrough here is recognizing that this is fundamentally a categorization problem. You're not sorting, you're not filtering, you're sorting items into labeled buckets based on a ruler that the caller, or you, defines. The rule is in the function, or the fn, right here. You don't know what the rule will be ahead of time. You just know call function on each item. Whatever string it returns is the bucket name for that item. Once that clicks, the structure almost starts to write itself. So you loop through the array, you call function on each item, and use the return value as the key in your result object. This problem contains an interesting wrinkle. So you're not just writing one standalone function, you're attaching a method to array prototype, which is right here at the top. Array prototype is essentially the shared blueprint for all arrays. When you do array prototype group by function, you're saying add this behavior to every array that exists. Inside that function, this, the word this that's right here, refers to the array the method was called on. So this is your array to loop through. The solution builds the result object incrementally as it loops. So for each item, we call function item to get the key. If that key doesn't exist yet, and as you can see here, there's this universal not operator that we spoke about in the concepts video. So if the key doesn't exist yet, then we create it as an empty array. Then we push that item into the array. And that's basically it. You're checking and creating the bucket on demand. You never have to know the keys in advance. The function fn tells you the key at the moment that you need it. So the loop is clean, the logic is minimal, and the function fn does all of that categorization work. Your code just organizes the output of that function. Moving on to the next problem, which is execute asynchronous functions in parallel. So you're given an array of functions, and each function returns a promise when called. Your task is to execute all of them in parallel and return a single promise that resolves when all promises finish, returns results in the same order as the input functions, and rejects immediately if one promise fails. You also cannot use promise all, so you have to build that behavior yourself. The main idea here is understanding what parallel execution means in JavaScript. Even though JavaScript runs on a single thread, we can still start multiple asynchronous operations at the same time. So instead of waiting for function 1, then function 2, then function 3, which is sequential, we do start function 1, start 2, start 3 immediately, then we wait for all 3 of them to finish. The important realization here is that parallel means initiate all promises immediately, not running them simultaneously in separate threads. So this challenge isn't creating promises, it's coordinating them. So we need to track when each promise resolves, we need to store the results in the correct order, we need to know when all of the promises are finished, and then we need to handle early failure correctly. So we build our own version of promise all using a results array, a counter, and an outer promise wrapper. This solution, as you can see right here, we create a new promise that wraps everything. Inside of it, we pre-create a new array called results. And this stores our outputs in the correct order. Then we loop through each function and immediately call it, which starts all promises right away. When each promise resolves, we store its results in the correct index. When each promise resolves, we store the results in the correct index, and then we increment the resolve counter. When resolved equals the total number of functions, we resolve the outer promise with the full array. And then if any of the promises reject, we immediately reject the outer promise. So the key idea here is we're not waiting for each promise individually, we are coordinating them centrally. So what's actually important here is not the syntax in this problem. It's the pattern of the coordination that's happening. So we start everything immediately, track completion manually, preserve ordering using indexes, and then fail fast on first error. This is essentially a simplified version of how promise all works internally. This connects directly to back-end work where multiple async operations may run independently. For example, fetching multiple resources, validating different pieces of data, or running independent database queries. Instead of doing them one by one, you can run them all in parallel to improve performance as long as they don't depend on each other. So let's move on to problem number 3, which is the LRU cache. So this problem is to design a data structure with a fixed capacity. So it should support 2 operations: get, which is the lookup of value by key, and put, which is to add or update a key value pair. The rule is, if the cache is full and you need to add something new, you evict the last recently used item, which is weird because in my mind it would be the oldest item, but it's the last recently used. So it's the one that hasn't been accessed in the longest amount of time. The hard constraint is both get and put must run in O of 1 time, meaning no matter how large the cache is, these operations should take constant time. So before jumping into this, let's first understand what O of 1 and O of n means as far as this problem is concerned. So the O itself, which is called big O, big O means how much work does the computer have to do as the amount of data grows. And then there are 2 things that we measure: time complexity, so how long it takes, and space complexity, which is how much memory it uses. So big O of 1 means the amount of work stays the same no matter how much data exists. So if imagine there's a wall of mailboxes. If I say go open mailbox number 42, you go directly to it. Does it matter if there are 100 mailboxes or 1 million mailboxes? Not really. You still do one lookup and one action. So accessing an array by index is usually O of 1, big O of 1, because JavaScript can jump directly to an index. It doesn't need to search through the whole array to find something. And then big O of n is linear time, so the work grows in direct proportion to the amount of data. So if data doubles, work roughly doubles. So for this, it's like imagine searching for your friend in a group of people. You may need to check the first person, check the third person, the fourth person, etc., etc. So the bigger the group is, the more checking is required. That's O of n. And then when talking about space complexity, it's the same idea but measuring memory instead of time. So big O of 1 space uses the same amount of memory regardless of the input size. So if there's a function that's adding one value to the next value, it doesn't matter how big the numbers are, the memory usage stays basically constant because you're only adding 2 things. O of n space is memory grows with input size. So if the function was asking us to double an array, then if there's 10 items versus 1,000 items, memory grows linearly, so that's O of n space. So if we're doubling something, the more we're doubling, the more space it takes up. Big O is not exact milliseconds or exact memory usage. It's more like a proportion or scale. So how does this scale as the data gets bigger? So looking at the problem, the first thing that comes to mind is just use an array and track recency by position. Move recent items to the front, evict from the back, but shifting items in an array is O of n, which is too slow. The insight here is that you need 2 data structures working together. So we need a hash map for big O of 1 lookups by key, and then we need a doubly linked list for big O of 1 reordering, moving nodes to the front and removing from the back. So the hash map stores keys and points to the corresponding node in the linked list. The linked list maintains the usage order. The most recently used item is always at the front or the head, and the least recently used is always at the back or the tail. And a hash map is like a direct address table. So you give it a key, it gives you a value immediately. There's no searching required. That's big O of 1 lookup. And then a doubly linked list is a chain of nodes where each node knows its previous and its next neighbor. Because each node has direct pointers to its neighbors, you can remove a node from anywhere in the chain in big O of 1. You can just update the neighboring pointers to skip over it. And why doubly linked? Because to remove a node efficiently, you need to update both the node before it and the node after it. A singly linked list only knows about the next node, not the previous one. So the pattern is every time you get or put a key, move that key's node to the front of the linked list, meaning it's the most recently used. When you need to evict, you remove the node at the back of the list or the least recently used. The hash map always points to the node in the linked list, so lookup stays big O of 1. So let's move on to our last problem, which is top k frequent elements. So for this problem, given an array of integers and a number k, return the k most frequently occurring elements. So if the input is 1, 1, 1, 2, 2, 3, as it is in example 1, and k is 2, the answer is 1, 2, because 1 appears 3 times and 2 appears twice. And the follow-up constraint at the bottom says that our solution should be faster of big O of n log n, where n is the array size. What this means is that it's ruling out simply counting frequencies and then sorting by frequencies. The insight for this problem is a technique called bucket sort, or in this context, frequency buckets. The key observation is the maximum possible frequency of any element is the length of the input array. So a number cannot appear more times than there are numbers in the array. That would be impossible. So that means that frequency values are bounded between 1 and n. So instead of sorting by frequency, which is that constraint big O n log n, you can create an array of buckets indexed by frequency. So bucket at index 3 holds all elements that appear exactly 3 times. Then you can just scan from the highest frequency bucket down and collect until you have k elements. The scanning step is big O of n, which brings the whole solution to big O of n, which is better than sorting. First, we count how many times each element appears. A hash map or a JavaScript map does this in O of n, which is just one pass through an array. Then, instead of sorting the map entries by frequency, you place them into pre-indexed buckets. This avoids the log factor in sorting because you're using position in an array as the sort order. So step 1 is one pass through the array builds the frequency map, and every element maps to its count. Step 2, one pass through the frequency map fills the buckets. Each element goes into a bucket at index equal to its count. And step 3 is scan from the highest bucket and index down, collecting elements until you have k of them. Because higher index equals higher frequency, you naturally will collect the most frequent first. So looking at these 4 problems together, a few patterns show up more than once. So hash maps appear in 3 of 4 of the problems. In group by, the result object is essentially a hash map from group keys to arrays. In the LRU cache, the map is what makes O of 1 lookup possible, and top k frequency. In the top k frequent, the frequency map is the foundation of the whole solution. The recurring theme is when you need to look something up quickly without searching, a hash map is usually part of the answer. And then understanding what constant time means mattered for LRU cache specifically. So O of 1 isn't magic. It's about choosing a data structure that gives you direct access. That's the whole point of combining a hash map with a linked list. Each structure does what the other cannot and fills the gaps. In my backend project, async await was about making sequential asynchronous operations readable. The promises problem is about parallel asynchronous execution, which is the other side of that same coin. Working through this LeetCode problem helped me understand why promise all exists and then what it actually does under the hood in incremental steps like this. The biggest thing I got from these problems was understanding that data structure choice isn't just about storing data, it's about what operations you need to be fast. For LRU cache, the whole design is driven by the big O of 1 constraint. If that constraint didn't exist, a simpler solution would work, but because it does, you have to think about what structure gives you constant time access and constant time reordering. For the other 3 problems, the lesson was more about pattern recognition, grouping data into a map by key, running promises in parallel, counting with frequency buckets. Those are all variations on the same underlying idea, which is organize your data in a shape that makes the next operation easier. And that's what I'm trying to build here, is not just the code, but the pattern recognition and the ability to problem solve when I pick up certain keys that remind me of certain things. I believe this is what they call critical thinking skills. So that's all I have for this video. Thank you for watching, and I will see you on the next one.